So, first we're going to start off by reviewing the vertical line test. Why do we perform the vertical line test? Yes, to see, to verify, a graph or a line on a graph is a function. Oh my God. So we're going to draw, let's draw a polynomial. Just some random funky looking thing. Does this pass our vertical line test? Yeah, it does. As I pass the vertical line over my graph from left to right, my vertical line never touches my graph in more than one place. So yes, it passes the vertical line test. I'm going to introduce something to you that is very similar, but instead of having a vertical line, we're now going to have a horizontal line. Now, when we take a horizontal line and we're performing what is called the horizontal line test, instead of going left to right, obviously you can't really take a horizontal line left and right. You're going to go from bottom to top. Does anyone know what it means if a function can pass a horizontal line test? There it is. Yes. We perform the horizontal line test to see if the inverse is a function. So here, yes, this current line, that like reflected cubic function, does pass the vertical line test. It also passes the horizontal line test. Because if I think of a horizontal line moving upwards over our graph, it never touches our cubic in more than one place. Therefore, the inverse is a function. If we take a look at that first polynomial we drew, is that function going to pass the horizontal line test? No, it's not. If I draw a horizontal line like this, it intercepts in multiple places. It for sure does not pass the horizontal line test. What does this mean? Good. The inverse is not a function. I shouldn't eat. Okay. So I don't want us to look back at these notes and be like, why is she drawing a horizontal line when we were supposed to be doing the vertical line? So I'm also going to draw the vertical line. We were just performing the horizontal line test here. Okay. And just a quick little definition. If a function is determined to be one-to-one, if a function is determined to be one-to-one, it passes both the vertical line test and the horizontal line test. One-to-one just means that for every x value, there is a single y value. And for every y value, there is a single x value. Everything goes one-to-one. Well, if you look at that cubic function, doesn't that pass both the vertical and the horizontal? Yeah. Radical functions. Mm-hmm. Exactly. So rational functions would be considered one-to-one. Okay. So now let's actually talk about inverses. Before we read that, actually, when I say the word inverse to you, what goes through your brain? Blankness. No. No. What do you think about when I say inverse? Yeah. Yes, that's one of the things I was about to go over. Whenever we're finding inverse functions, we can think of them as being reflected over the line y equals x, always. Because along the line y equals x, those points will not move. Now, if I give you a point, say, I don't know, let's see, -2, 1. And I told you find the inverse point, what would you tell me? 1, -2. How did you get that? Right, so there's two ways to think about it. Either reflecting over that line, y equals x, or we just switched the x and the y value. That's all we did. And in general, in its entirety, when you hear the word inverse, I want you to think immediately, switch x and y. Switch x and y, switch x and y. Almost everything having to do with inverses flows from the concept that you are switching the x and the y. Hey. So up here I'm going to write, because I want it to be one of the first things you see on this page. Whoops. Inverse. You should immediately think, switch x and y. Almost every logic, everything that has to do with inverses can be derived from the concept of switching x and y. And that's what this big log definition is trying to tell you, that if you have an ordered pair AB, then the inverse pair is going to be BA. I don't know why they didn't just put switch x and y, but you know. Okay, also a little bit more about inverse functions. So I do have an inverse point here. I'm going to create a line from this point. I'm going to create kind of like this half of a, well, no, let's not do that. Oh, God. Oh, my goodness. You know what? We're just going to do that. All right. So I'm going to create this line right here, this radical. That's what a radical function looks like. From a starting point, it kind of looks like half of a curved quadratic. This is our original function. F of x, we'll call it. What is the inverse function going to look like? How should I draw my inverse function? Good, so we know it's going up to the, so no, because radical function, oh my goodness. Radical functions don't actually have asymptotes. This one kind of looks like it does, but it does not. So this would be our inverse function. You think of it as a reflection over the line y equals x, like you're folding your paper over the line y equals x. And we always denote inverses with that exponent of -1 on the function. So that's f -1 of x, f inverse. Okay, so that's just some little things about inverses. Also, it says right here, the inverse function has a domain R and a range D, where the original function had a domain of D and a range of R. What does this mean? Exactly. So, again, this concept flows from the idea that we're just switching the x and y values. If we switch all of the x's, which is the domain, with all of the y's, which is the range, this means that the literal domain and ranges switch. So we're just switching the domain and range for the inverse. So if our original function had a domain of D and a range of R, our inverse function is going to have what? Good. A domain of R and a range of D. They swapped places. The x and y swap. All of the x's swap with all the y's. And we'll get more into that in a second. Okay. We're now going to be solving for inverses algebraically. So we can find them on the graph by reflecting over the line y equals x. But we also need to know how to find them algebraically. Now we know that inverses, to create an inverse, you just switch the x and y. Same thing algebraically. In the equation, we're going to switch x and y. Dylan. Okay, so we have 3 steps here for finding the inverse algebraically. Now what they don't say, and I like to call this my pre-step, if we have a function defined as f of x, or in any sort of function notation, we need to first change f of x to y. That's our first pre-step. Change f of x to y. Because we then, in step 1, have to literally switch the x and y values. So wherever we see a y, we're going to write x instead. Wherever we see an x, we're going to write y instead. Step 2 is solving for y. Step 2, we solve for y. Get y all by itself, that means. Get y by itself. And the final, last housekeeping thing we have to do is change y back into function notation by writing f inverse of x, or f -1 of x. So let's try it. I'm actually going to do example 2, and then example 1, and then we'll talk about inherited domain for example 2. The reason I'm doing this is because example 2 is a lot easier than example 1. I'm trying to find my inverse function for f of x. What should I do first? Yes, change that f of x out for a y. That's my pre-step. Then what do? Switch the x and the y. So we'll have an x out in front this time and a y inside the square root. Now we're trying to get y by itself. What should you do? Square both sides. Yes. Opposite operation of square root is square. So the square and the square root will now cancel. And we have x squared is equal to y plus 3. Then what? Yeah. We need to get y by itself, so we still need to subtract that 3 away from the y. And we have x squared minus 3 is equal to y. What is the final thing we have to do? Yes, change the notation. Change that y back into function notation here. F negative 1 of x is equal to x squared minus 3. And this is our inverse. Any questions on this one? Okay. Now let's take a look at this one. We're going to find the inverse. First, change the f of x out for a y. Okay, where are our 6? This is 4th period, right? Dhruva, what do you think I now do? Yes. Now, just because there are 2 x's, don't let that screw you up. We're still just switching x and y, meaning wherever I see a y, I'm going to write x. And wherever I see an x, I'm going to write y. Okay, I was going to pull 6 for this, but I'm realizing I don't think I want to put people on the spot so much for this problem because it does get a little tricky. So I'm just going to ask, what do you think we now do? Close. We want to get rid of the fraction, right? So in order to get rid of a fraction, we just multiply both sides of this equation by the denominator. The y plus 1s will cancel on the right. And what am I left with on the right, Aiden? Yeah, just a y. What do you think I should do on the left? Anybody? Exactly. You're distributing that x in. So we have xy plus x. So now this is where it gets a little tricky because you're like, okay, we still have 2 y's here. We don't have y by itself because there's a y on the left-hand side. My suggestion to you, okay, we at least need to group the y's together on one side. So what do you think I should do? Can I divide by y yet? No. Yes. Subtract xy to the other side. These can't be combined. It just remains y minus xy. Now, does anyone notice anything here on the right-hand side? Yes. You can factor GCF out of that right-hand side. What GCF can you factor? Oh my gosh, you can pull the thing we're trying to get by itself away from everything else. That's perfect. I'm going to factor out a GCF of y. What am I left with? And if you know you're going to forget that, which if I was in high school, I would know I'd forget, I'm going to write, I just factored out or pulled out a GCF of y. Not GFC, Miss Sunderland. GCF of y equals x, right? Can't forget that. All right. Y is still not all by itself. What should I do? Divide by 1 minus x. Exactly. What happens on the right? It becomes just y. And on the left, I have x over 1 minus x. And then what's our final housekeeping step here? Change it back to function notation as the inverse. And I'm done. I found my inverse. Whoop. Okay. All right. Any questions on this one? All right, we're now going to look at example 2. Because now we need to talk about what the heck this inherited domain means. First, what we're going to do to understand this inherited domain, we're going to go ahead and graph the original function. Just a quick little sketch. So our original function here had been square root of x plus 3. How can I graph this? Yes, you can create a little table, but if you remember anything about radicals or anything about transformations, what do you know about this graph? Where is it moved? It's moved 3 to the left. All right, so we know that the starting point at least has moved 3 to the left. Has anything else changed about this from the parent function? So what does a radical look like? It does go to the right and upward infinitely, like so. That's all I was really looking for here. We're just trying to understand this conceptually. So, knowing that this is the original, conceptually, we know to find the inverse, what are we doing to the graph exactly? Yes, we're reflecting it over the line y is equal to x. So, if I'm going to go ahead and graph my inverse, I know that if I had that point there that was to the right 3, meaning negative 3, 0, where's my starting point on my inverse? Oh my goodness, down 3 on 0. And where should I draw this line? Exactly, like this. What makes you stop and pause here? Right. Look at our inverse. What type of function is that? If I was just to look at this, I would think that the full graph of this is a what? A quadratic. But did I graph a quadratic? I only graphed half a quadratic. What was this? X squared minus 3. I just want to write this down. Why is this? Exactly. Exactly. That's perfect. In order to know why we only grabbed half of a quadratic here, we need to understand the domain and range of the original. What was the domain of the original function? Negative 3 to infinity, including negative 3. And what's the range? Beautiful. So, without knowing any background information about anything, just knowing the domain and range, pretend we don't know anything else about this problem. What is the domain of that inverse? Yes, it's the range of the original. So 0 to infinity, including 0. And what's the range? Negative 3 to infinity, including negative 3. Which is exactly what we have graphed here. This is called an inherited or imposed domain. I like to call it imposed. Either vocab word is just as accurate, but this is called an imposed or inherited domain. If we just look at what the inverse is, we would inaccurately draw this inverse. It instead has an imposed domain, a restriction that isn't necessarily originally there for that line. Does this make sense? Did I lose anybody? Does anybody need some extra explanation here? Okay, let's go the reverse way. Now it wants us to draw the parent function of a quadratic and then draw its inverse. So now instead of going from a radical to a what we thought was a quadratic, we're now starting with a quadratic and we're seeing what happens. So where's the vertex? Where's the vertex on x squared, our parent function? 0, 0. From here, we know our parent function hasn't been shifted, hasn't been stretched or compressed or reflected. Where are the next perfect points? Yes, up 1 over 1, which is at 1, 1, and also the mirror image of that, negative 1, 1. Let's do one more set. If my x value is 2, what's my y value? Good, I have to square it to get my y value. And the mirror image point is also created. So that's my quadratic. And I'm going to list these points, coordinates from left to right. I have a negative 2, 4. I have a negative 1, 1, a 0, 0, a 1, 1, and a 2, 4. Again, it's not necessary that you know how to graph this just from memory, as long as you can input x values and output y values. Okay, so before we graph this, we're first going to find those coordinate points based on the table. So I'm finding the inverse coordinate points. Okay, Our first coordinate point created by the inverse is what, Julian? If I'm just starting at the top of my table and taking that point, negative 2, 4, what will the inverse point be? Yes, 4, negative 2. Which, I'm just going to go ahead and start graphing these. 4, negative 2, right there. What will our next coordinate point be, Ainsley? Yes, 1, negative 1, which is here. What about the next point, Shashank? There, 0. Shashank, you have so many voices. Oh, blank stick. What about the fourth point, Zachary? 1, 1. And both of those points remained in the exact same place because they're along the line y equals x. Eddie, what about our last point? Beautiful. And I connect these points. Now, what do you notice immediately? Not a function. It is not a function. So no, the inverse is not a function. Why? How do you know? It does not pass the vertical line test, VLT. How else could we have known the inverse would not be a function? I see over there, hand, way in the back. We could have performed the horizontal line test on the original, and it would have already told us, no, the inverse is not a function. And the original function, OG function, does not pass the horizontal line test. Any questions here? Okay. So now we have to go about proving. Just like we proved, what did we prove? What have we proved? Odd and even, that's right. Just like we had to algebraically prove odd and even, we have to know how to algebraically prove that functions are inverses of each other. Now, look back up here. You don't have to flip to your page, but what about these tables told us that these were inverse functions? Yes, Uma. Exactly. Whenever the initial input x is equal to the composition of two functions, this is what automatically tells you that those functions are inverses of each other. So when I go about algebraically proving that two functions are inverses of each other, this is what I need to show. I need to show that f of g of x is equal to x, but also that the other composition, g of f of x, the reverse, is also equal to x. This is because there are some scenarios, only very, very few, but there are some scenarios where, yes, f of g of x will equal x. Great. But then you go and check g of f of x, and it is not equal to x. You have to check both, all right? So let's do it. Let's go ahead and prove that f of x and g of x are inverses here. You need to check both. Doesn't matter which one you start with. I'm going to do f of g of x first. What does this mean? What am I doing? Exactly. I'm taking all the g of x's, and wherever I see an x in f of x, I'm replacing it with g of x. So I have parenthesis the square root of x plus 2 minus 2 squared. What do I do first here to simplify this? Look, we have a plus 2 minus 2 inside of those parentheses. They cancel, leaving us with the square root of x squared. What do you notice now? We have opposite operations here. Whenever you square a square root, they cancel. They're opposite operations. And I'm left with just what? X. So guess what? The first one checked out. So far, so good. So far, these are inverses. But now I need to check g of f of x. So now I'm taking all that f of x is. Oh, I didn't recognize or notice this before. They forgot to put the f in front of f of x.
I was just looking at that.
Oh, you're like, if x, what? Okay, so we're taking all of f of x, and wherever we see an x and g of x, we're writing all that f of x is. So I have the square root of x minus 2 squared plus 2. What do you notice here? Yes, again, we have opposite operations that will cancel, leaving us with what? Good. And then what do you notice? Yes, minus 2 and plus 2 cancel. So what does this mean? They are inverses of each other.
What is in the example where x is greater than or equal to 2?
So it's just stating that we aren't looking at the values where x is less than 2, because then technically we wouldn't have an inverse here. So it's kind of extra information in this process. We're just trying to prove that these are inverses. This restriction technically won't change our answer. All right. Okay, so f of g of x is equal to g of f of x, which both are equal to x, meaning that yes, these are inverse functions. What? All right, guys. So bear with me. Bear with me for this problem. This is a beast of a problem. And yes, you have something like this on your Math Excel. So let's just dive right in. I can hopefully get it done in 9 minutes. We need to prove that these are inverses by finding their compositions, just like we did before. So first I'm going to take all the g of x's, and wherever I see an x, I'm going to replace it with g of x. So I have 3x plus 5 over 1 minus 2x, all subtracted, all of that minus 5. over 2 times 3x plus 5 over 1 minus 2x plus 3. Whew. Okay. So again, what makes this problem hard is not the composition, but the simplification. Just like we had to last class, it's a very similar process. In order for this to be simplified, what do I need to do? Yes. We need to, our first goal is to get a common fraction in both the numerator and the denominator. So I'm going to multiply this 3 by something that forces it to have the same denominator as the other fraction. So I'm going to multiply it by 1 minus 2x over 1 minus 2x. I have to do this crazy fraction because I can only multiply by something that's equivalent to 1. And I'm not changing the value of the 3. I'm just multiplying by 1. Now, what makes this problem different than the problem we had last class with compositions is that we also need to get a single fraction in the numerator as well. So I also need to multiply this 5 by the other fraction's denominator. So now, in order to start combining all these fractions, I do first need to distribute the whole numbers into the numerator. I know, just bear with me, bear with me. So we end up with 3x plus 5 over 1 minus 2x. This is the only fraction that remains the same. Now I'm going to go ahead and distribute that 5 as a negative 5. I'm going to distribute the negative as well, meaning between these two fractions becomes positive, and I have negative 5 plus 10x. I do this just to make sure that I'm not screwing up my negatives in the end, because that'll be the most commonly missed part of this whole thing, is if there's a negative, you'll forget to distribute it. Then in the denominator, I'll have 6x plus 10 over 1 minus 2x plus 3 minus 6x over 1 minus 2x. What should I now do? What should I now do? Yeah, I did all that so that I can combine these fractions. And we combine fractions by adding the numerators. The denominators will remain the same. What are my like terms in the numerator? (3x) and negative 10x. What else do you notice happens? 5 and negative 5 cancels. So I have what in my numerator here? 13x. My denominator remains the same, 1 minus 2x. All over, what happens in the denominator's numerator? The 6x and the negative 6x cancel. What else? (3 plus 10, and we get 13. And my denominator remains the same, 1 minus 2x. Okay, so now we have a fraction over a fraction. How do I simplify this great big fraction? Yeah. Good. So what we need to do is multiply the numerator, which is 13x over 1 minus 2x. Multiply that by the reciprocal of the denominator, 1 minus 2x over 13. And what do you notice? These are now 13x times 1 minus 2x and 1 minus 2x times 13. We now have multiplication of terms in the numerator and denominator. What can I now do? Because I have multiplication, what can I do? Cancel like terms. What like terms cancel here? 1 minus 2x completely cancels. What else? 13. What am I left with? X. Whew! All right. So you do also need to do g of f of x. I'll leave that to you. I will have it, or I do have it written on my key.